All right, hello, and welcome to video number 3 of section 5.5, I should say. This video is going to be all about that matrix on the board behind me. The matrix C equals A, negative B, B, A, where A and B are both real numbers and both not zero. Well, sorry, and are not both zero. So either A or B could be zero, but not both. So you could have one of the two being zero. Why do we want to talk about this matrix, you ask? Well, let's see why. So first I want to calculate the eigenvalues of C. In the worksheet, I believe I have the eigenvalues listed, but I'll tell you them after we calculate them here. Well, with most matrices, we're going to do this in the following way by calculating the determinant of C minus lambda I. And so this is equal to A minus lambda squared plus B squared and I think if you factor that out, let me check my notes to make sure I got that right. Yes, that's what you get. So finding the eigenvalues of this matrix, we're going to have to use the quadratic formula again. And this time around, I will not sing it. At this point, it is already too possible that I'll have a family member find my YouTube channel and watch a video of me singing the quadratic formula. So I will just write out the quadratic formula, but know that I am singing it in my head as I write this out, as I almost always do. It's amazing how jingles, right? That's why jingles are so successful in, for like selling things, right? Because you just remember the jingle. And so this is like the quadratic formula jingle. It just gets stuck in your head. So anyways, simplifying this wonderful equation, we get negative 4b squared all over 2. And so the 2 cancels out here. You can pull out a 4 and a b and a negative I, or an I. And so you can actually show that this simplifies down to A plus or minus BI. And so C has 2 eigenvalues, A plus or minus BI. And so I realize now number 2 actually on this we've kind of already seen, but I'll redraw this because this picture is going to be extremely important for what we're about to talk about. So remember again, we're here, this is the real part, this is the imaginary part, and we'll pretend that this is the point AB. And so remember that the length of this line, let me make that a little more line-like. The length of this line is equal to the modulus of lambda. So remember that this is equal to length of line formed by origin and AB, which is just equal to, remember, the square root of A squared plus B squared. So keeping this in mind, right, we can start to talk about, well, the length of this line, which I'm going to call R, and the angle formed by the line and the x-axis, which I'm going to call phi. So it turns out, as we're about to see, that, remember, we can talk about matrices as linear transformations in the two-dimensional plane. So if you remember in section 1.9, I want to say it was, we looked at all these different types of rotation, scaling, and matrices of the sort that we kind of talked about like how those matrices work and, kind of like how they, can take points in the plane and rotate them, scale them, do whatever. And so what I actually want to show is that it turns out that every complex matrix is somewhat of a rotation and a scaling in the two-dimensional plane. And so we're going to start by looking at this specific matrix C of the form A negative B, B A. And notice we've calculated that basically as long as B isn't equal to 0, this matrix has complex eigenvalues. And so I'm going to convince you that this matrix is actually going to take every point in the plane, scale it by r, and then rotate it by this angle phi, where here r is the modulus of the eigenvalues of C, and phi is the angle of rotation formed by the origin and this line r corresponding to the modulus. All right, so why is that? So first we can sort of look at an example of what this matrix does to the point 1, 0. So I'm going to keep a few things handy here while trying to create some space. So we'll remember that lambda is equal to a plus or minus bi, and that r is equal to the modulus of lambda. And notice specifically that it actually doesn't matter which one of the two eigenvalues, a plus bi or a minus bi, we use in calculating r, that because it's just a plus b squared, we're going to get the same modulus for each of the two eigenvalues. So we can just look at a plus bi for now. And so, or we can look at a plus bi, I guess, when calculating the modulus. So let's see what C does to the point 1, 0. So remember, as a linear transformation, we're going to multiply 1, 0 times this. Well, and this isn't terribly exciting, but we get the vector AB. And so let's look at what happens now maybe in the plane. So maybe say the point 1, 0 is here. So notice what it does is it takes this point, scales it out to have length r, and then it rotates this point up around this circle by phi. So it takes, and notice then that doing this gets 1, 0 to the point AB. So C sends the point 1, 0 to the point AB by scaling it so that it has length r, and then rotating it around sort of the circle defined by this point r0 at an angle of phi. And so that's how it sends 1, 0 to the point AB. And so it does this to all the points in the plane. It's just easiest to see when we look at what's happening to the point 1, 0, because it's kind of easy to picture where the point 1, 0 is going. So expands by r, or if r is potentially less than 1, contracts so that the length of the original line has length r, and then, or multiplies it by r, I guess I should say, right? So here, the length of this line was equal to 1, so it multiplies it by r, scales it by r, and then rotates it by an angle of phi. So why does it do this in general? Well, we can actually rewrite C in the following way. So notice that I can, in a sense, factor out r from this matrix like so, right? All I did was just pull the factor of r out of each term, and it doesn't even matter if the terms are divisible by r, right? I can just do it. Well, so it turns out that if we were to multiply these two matrices, remember multiplying this matrix times this matrix is actually equivalent to multiplying r times this matrix, right? So multiplying r by each one of these terms is equivalent to multiplying the identity matrix times r and then doing this multiplication, right? And that's because this matrix is just the identity matrix times R. Well, so if you'll remember now from section, if you go back and look at the adventures of the square in the two-dimensional plane, this is actually just a scaling matrix that scales by R. So we've decomposed C now into the product of a scaling matrix, R0, 0, R, and this matrix. But now I want to, for a brief moment, recall the definition of sine and cosine of an angle. So I'm going to, for the moment, erase what's going on to 1, 0, and we're going to just look at this triangle again. I guess I should say for a brief moment, I'm going to permanently erase what's happening to 1, 0. So notice that the length of this line has length A. The length of this line has length B. And of course, the length of the hypotenuse of this triangle has length R. So this is a line of length A. This is a line of length B. This is a line of length R, where of course R is equal to the square root of A squared plus B squared. So the Pythagorean theorem has not been disproven today. I don't think it'll be disproven ever, in fact. Okay, what is the cosine of this angle? Well, cosine is the adjacent side divided by the hypotenuse. So the cosine of this angle is equal to what? A divided by R. The sine of this angle is equal to opposite over hypotenuse, which is equal to B divided by R. So notice that, in fact, this is not only the product of a scaling matrix and a matrix with a bunch of meaningless fractions. This is the product of a scaling matrix and a rotation matrix rotating by phi. And so if you go back to section 1.9, this is actually a rotation matrix by phi. And so as it turns out, exactly what we saw happening to the point 1, 0 is in fact happening to all the points. That every matrix of this form with complex eigenvalues A plus or minus bi is in fact taking every point, rotating it by phi around its axis, and then scaling it by R. And I think you could actually show it, so I did scaling by R, then rotating it by phi, right? At this step, you could move R over here, and in a sense, you could move that matrix over and you'd still get the same, thing. But so notice, every matrix of this form is a rotation matrix multiplied by a scaling matrix, and so it's taking every point in the plane, rotating it, and then scaling it. And that's so cool. Every matrix of this form is doing that, where here the angle phi is calculated like so, and the radius r is calculated, or the, I guess, scale factor r is calculated to be the modulus of the eigenvalues. And I don't know, it's just so amazing how that stuff ends up working out. But so I've claimed we can actually do more. I've claimed we can actually show that, in fact, every complex matrix is, in a sense, a rotation and a scale. So keep this in mind, and we're going to go back and we're going to look at the first example we looked at in this section. So we're going to look at our familiar matrix A, which we now know all of the eigenvalues and the eigenvectors for. So then we know A has eigenvalues. And I'll list them separately here because I want to specifically look at one of the eigenvectors. And I have to quickly remember which eigenvector. So this is the eigenvector for 2 plus I. And the other eigenvalue was 2 minus I. With eigenvector, actually I guess it doesn't matter which for the purposes of this example, but v1 corresponding to lambda 1. So the eigenvector was equal to I minus 1, 1. All right, so we're going to define P to be the following matrix. Be the matrix whose first column is the real part of V and whose second column is the imaginary part of V. And so this is V1, excuse me. And so notice here the real part of V1, oops, this should be I minus 1. That looks too much like I minus I, is the vector negative 1, 1. And the imaginary part of V1 is the vector 1, 0. And so certainly looking at these two columns, they are not linearly dependent, right? So we know that P has linearly independent columns, meaning that P is invertible. Maybe you already can kind of see where I'm going with this, but if you want to calculate the inverse of P, well, this should be, the determinant of this matrix is negative 1, so this should be the matrix 0, negative 1, negative 1, 1. We can double check that. That's not quite right. Positive 1, 1. So this matrix. That should be the inverse of P, right? So do the matrix multiplication dance. That gets us a 1. That gets us a 0. Let's see. So then that's not quite right. Well, no. So then that gets us a 0. That gets us a 1. Yeah. So that's P inverse. Okay, so remember, if I have any invertible matrix P, I can use P as a similarity transformation for the matrix A. So what we want to do is calculate the matrix, and I have to make sure that I think the order of these matrices might matter. So P inverse A P. And let's see what we get. So this is 0, 1, 1, 1 times 1, negative 2, 1, 3 times negative 1, 1, 1, 0. So I'll go left to right here. So we'll do this matrix times this matrix. 1, 3, 2, 1 times negative 1, 1, 1, 0. Now, this is 2, 1, negative 1, 2. So what do you notice about this matrix? All we're doing, so this matrix is similar to, and if you remember, we've already sort of shown that similar matrices represent, in a sense, the same linear transformation, just represented under a different basis, right? This is a matrix of the form, so if we let A equal 2 and B equal negative 1, then this matrix is equal to A negative B, B, A. And so as we can see, this matrix is a matrix with the same eigenvalues as A, which it should have the same eigenvalues because we just showed it similar to A. Same eigenvalues as A. And this is a matrix which is performing a rotation and a scaling. And so it turns out that every complex matrix in this way is a rotation and a scaling. it's just, you know, if the matrix isn't already sort of this almost symmetrical matrix in this way, that we first have to change the variable using this similarity transformation P. And so you can actually look at pictures of this in the book that turns out with this matrix, because P sort of is changing the variable here, or changing the basis here, we don't get this nice circular transformation that we would get with a matrix C like this. The transformation turns out to be elliptical. So if you look at the axis of sort of what's going on, you end up getting an ellipse with this axis instead of a circle. But so as it turns out, using this similarity transformation, every 2x2 matrix with complex eigenvalues is, in some way or another, a linear transformation that involves a rotation and a scaling. Awesome. So I'm going to state that as a theorem, and then we're going to do one more example to wrap up this section. And basically, this theorem is just going to state exactly what we just showed, but in general. So this is theorem 9 in your book. So if A is a 2x2 matrix, with a complex eigenvalue, and notice here, all we need to do is find one complex eigenvalue to guarantee that this all happens. And so here we're going to assume that B is non-zero to make sure this is actually a really complex number, not just, you know, a real number. And an associated eigenvector V in the complex plane. Then we know that A is equal to P C P inverse, where P is the matrix that we just defined, whose first column is the real part of V, second column is the imaginary part of V, and C is this rotation scale matrix that we've already seen, A, negative B, B, A. And so that's sort of the big result of this section, that it turns out every matrix with complex eigenvalues is a rotation and a scale. So I want to finish with one sort of concrete example. So we're going to let A equal the following matrix: root 3, negative 1, 1, root 3. And so notice A is already of this form, right? So we know that A is going to be a matrix with complex eigenvalues and a matrix that involves a rotation and a scale. And so we know that we're going to be able to write A in the form R0, 0, R times cosine phi, negative sine phi, sine phi, cosine phi. And so what we want to do is first find the eigenvalues of A, then find this scale factor R, and we'll finish by finding the angle of rotation phi. So to do this, I have to remember my trig. So first, the eigenvalues of A are actually fairly straightforwardly given to us to just be by the fact we'd previously stated. The eigenvalues of A are just root 3 plus or minus I. And so actually then R kind of immediately follows because it's the modulus. So this is equal to root 3 squared plus 1 squared, which is the square root of 4, so equal to 2. And so we can actually immediately fill in here 2 for R. And so now remember, we want to find this angle phi. And to do this, I like to draw a picture to remind myself exactly what's going on. So what we want to do is we want to look at here this point, root 3 1. And remember here that r is equal to 2. Right? So this is a triangle, x-axis length, or x length root 3, y length 1, hypotenuse length 2, and that the angle phi goes there. And so if we want to find phi, we just either need to look at the cosine of phi or the sine of phi. And remember, the cosine is equal to the adjacent side over the hypotenuse. So we know that the cosine phi is equal to root 3 over 2. And then using our trig and knowledge of cosine inverse, the angle whose cosine, angle between 0 and 90 degrees, whose cosine is root 3 over 2, is the angle pi over 6 radians. So it turns out that this matrix, eigenvalues root 3 plus I, takes every point, scales it by a factor of 2, and then rotates it pi over 6 radians with respect to the origin. So that is complex, or that is all of, actually the end of chapter 5. So tomorrow we'll move into section 6.1, and that's complex eigenvalues. Just so awesome.